Giglio Power Infrastructure Engineering. In this video, I show how I used COMSOL Multiphysics to model a single 3-core cable heated in air and use the opacity in the manufacturer's datasheet to complete a temperature run to validate the setup of the model. For this example, the selected 3-core cable is by BAHRA Cables and the ambient air temperature is 40 degrees Celsius. And for the cable laid in free air, the opacity is 635 amps and the cable dimensions are as highlighted shown here. Here is a temperature surface plot of the 3-core cable heated in air. The opacity value of 635 amps from the manufacturer datasheet was used in a temperature run, and the maximum conductive temperature reached 89.3 degrees Celsius, which is 1 degree less than the temperature limit of 90 degrees Celsius. Here is a plot of conductor temperature versus time. The initial conductor temperature is 40 degrees Celsius and rises to the maximum conductive temperature below the temperature limit, about 89.3 degrees Celsius. And here's the view in a semi-log plot. Probes were used to measure the maximum conductive temperature on the insulation boundary and measure the maximum temperatures of the screens and sheath. These temperature variables were used in the IEC equations to compute the heat sources that are used in the heat transfer in solids and fluids interface. Here, the heat sources are applied volumetrically for the conductor, dielectric, screen, and sheath. Infinite element domains are applied to the exterior air domains, and ambient temperature of 40 degrees Celsius is fixed to the exterior boundaries. For the surface-to-surface radiation physics interface, only the cable's exterior jacket boundaries are selected. The jacket domains are set to opaque, and the air domains are set to transparent. Part of the heat generated in the cable will transfer out radiatively due to the temperature difference of the cable's exterior boundary and the ambient environment. The remaining part of the heat generated in the cable is transferred out convectively due to natural convection as determined by the laminar flow physics interface. Here, compressibility is set to weakly compressible flow. Include gravity is checked. Gravity's direction and magnitude is specified. A pressure point constraint is applied in the fluid. An open boundary condition is applied to the bottom boundary and top boundary. And to facilitate convergence, instead of using an open boundary for the sides, a wall slip condition is applied and is justified since fluid is really not crossing these boundaries and there are no viscous forces. The reliability and accuracy of this model has been validated since the manufacturer's opacity value was used in a temperature run and the maximum conductor temperature was very close to the temperature limit. Here is a view of the mesh. The average element quality is 0.8984. Boundary layers were used to capture the large temperature gradients. Contact Giglio Power Infrastructure Engineering if you would like detailed and fully coupled multi-physics solutions using FEM and CFD for any power cable system of any complexity. We have novel methods to directly and accurately compute opacity of any type.